In this video, I'm going to write a rigorous formal proof for a theorem about sequences, specifically that every convergent sequence must be bounded. Here is the theorem, written as formal as I can. Let A n be a sequence. If it is convergent, then it must be bounded. It's just a one-sentence statement. The proof will naturally use the definitions of these two concepts, so let's recall them. Saying that the sequence is bounded means that there are two real numbers a and b, and the sequence is always between them. So for every natural number n, an is between a and b. That's what it means to be bounded. That's what I want to prove. On the other hand, saying that it is convergent means that there is a real number L that is the limit of the sequence. And here is the formal definition of the limit of the sequence is L. It's this long statement with many quantifiers. But there is one particular aspect of the definition of convergent, which is what I'm going to use. A way to summarize what it means to be convergent is that all terms of the sequence except the first few ones are close to the limit, or if you prefer, except finitely many. And this is what encapsulates the proof, because if all the terms of the sequence are close to the limit, then the sequence must be bounded. And now if it's all the terms except for just a few, for finitely many, for 10, the sequence will still be bounded. In order to be unbounded, I need infinitely many elements in the set conspiring together. Well, let's turn this idea into a rigorous proof. First, I'm going to look at what the structure of the proof should be like. Then, I will do some rough work to figure out the details, and then finally I will write a formal rigorous proof in the correct order. What will the structure of the proof be? Here is again the definition of bounded. I want to show that there exist real numbers a and b, such that for every natural number n, a is less than or equal than an, less than or equal than b. In my proof, I will begin by assuming the hypothesis that I have a sequence that is convergent. And then I need to prove that there exist real numbers a and b with a property. So after doing some math, I will say what a is and what b is. I have to prove they exist. The best way to do that is to say exactly what they are. After I've done that, I have to prove that something is true for every natural number n. So I will fix an arbitrary natural number n, and after doing some math, hopefully I will have concluded the inequalities. The key step is number 2. As part of my proof, I'm going to have to figure out what is A and what is B and say that exactly. Let's do some rough work to figure out what these A and B are. Here is, once again, the property that A and B need to satisfy. I'm going to focus first on how I construct A, how I come up with it. And then B will follow a similar construction. I'm going to be using the definition of limit because I know the sequence is convergent. So here is again the definition of limit of a sequence. And of it, I'm going to focus on the last part of this big statement, which I'm putting in red here. At the end of the implication, I see that the absolute value of an minus L is less than epsilon. We know that this can be rewritten in some equivalent ways. Specifically, we can say that an is between L minus epsilon and L plus epsilon. So I will copy the full statement, but replacing this last part with this equivalent thing. And now look at the part in blue at the top, that is what I want, and look at the part in red here, which is what I seem to be able to get. This suggests that I'm going to choose big A to be L minus epsilon or anything smaller. Because if A is less than or equal than L minus epsilon, which in turn is less than an, then A will be less than or equal than an, and that's what I need. However, there are two subtle points here still to observe. First, for this to be part of a rigorous proof, before I do anything, I'm going to need to choose one single value of epsilon. This big statement is true for every epsilon, so it will be true for my favorite choice. For example, I'll take epsilon equals 1 for simplicity, but I need to fix epsilon, otherwise this makes no sense. And second, what I got here is not true for every natural number. It's only true for natural numbers starting at n0. That means I also have a few more terms of the sequence to take care of before. So separatedly from this condition, I need to make sure that big A is less than or equal than A0, A1, and so on, but there are only finitely many terms to take care of now. And I know how to do that. I can simply take big A, look at all the conditions I need on it, they are in blue. I will take big A as the minimum of all those things. I can do that. The minimum of finitely many numbers is a number. If there were infinitely many conditions, then I wouldn't be able to say that because I don't know what the minimum of those is. But with finitely many conditions, that is fine. And that is it. That is the value of A I need in the proof, which was the most difficult step. A similar construction will work for B, and for B we will simply take the maximum of L plus epsilon and all those terms. So we have the right idea, we are ready. Now let's write it as a formal rigorous proof going in order from beginning to end. Let's begin the proof. I have a sequence that I assume is convergent. Therefore it has a limit. I'm going to call L the limit. Then, in the definition of the limit of the sequence equals L, I am going to choose epsilon equals 1. I could have chosen anything else, but I'd have to choose a number, and 1 is the simplest. Then from the definition of limit, we know there exists a natural number n0, such that all natural numbers after that satisfy that an is greater than L minus 1 and less than L plus 1. That's from the definition of limit. Then, having found this n0, I'm going to say what A and B are. I'm going to take A as the minimum of L minus 1 and those first few terms of the sequence. And I will take as B the maximum of L plus 1 and those first few terms of the sequence. Now I have to prove that for every natural number n, an is between A and B. Let's fix an arbitrary natural number n. There are now two cases to consider. The first case, if n is greater than or equal to n0. Then in that case, an from the first equation is between L minus 1 and L plus 1. And therefore, by construction of A, big A is less than or equal than L minus 1, and by construction of B, B is greater or equal than L plus 1, so an is between both of them. What's the second case? The second case is when n is less than n0, and in that case, directly from the definition of big A and big B, we have that an is between them. In both cases, I get the inequality I wanted, and that completes the proof. I have written some parts of the proof in blue. If you look at those are the summary of the structure of the proof. And you will see that it agrees with what we decided the structure of the proof should be before we started.